In the previous segment, I was talking about the power model, and here we have the sum of the square of the residuals. We want to take the derivative with respect to a and b and put those equal to 0 to be able to figure out what the values of a and b are. So let's go ahead and go about doing that. So we got del SR by del A is equal to summation I is equal to 1 to n. So when we're taking the derivative with respect to a, you get y sub I minus a xi raised to power b times minus xi raised to power b. That's what you're going to get when you're going to take the derivative with respect to a there. Now let's go and see that what am I going to get when I take the derivative with respect to b. Of course, this is equal to 0. When I take the derivative with respect to b, I get summation of I is equal to 1 to n 2 times again a xi raised to power b times the derivative of this whole quantity with respect to b, and that turns out to be minus a because there's a constant here, xi raised to power b times log of x of I equal to 0. Okay. So keep in mind that the formulas which I have used there are as follows from your differential calculus class. If I have u as a function of x, d by dx of u square is 2u du by dx. That's the formula which I use to get this 2, then the expression u, and then take the derivative of u. And the other one which I'm using here to get this expression here is simply this formula, d by dx of a raised to power x is nothing but log of x times x raised to power a raised to power x, like this. So this is the formula which you are getting for d by dx of a raised to power x. So let's go and see that we're going to simplify this a little bit further. So if I take this one here, let me see what I get there. I get this should be log of a. Should be log of a here. So let's go and see. If I simplify this, I get 2 here and now minus here. So I'm going to get 2 summation minus 2 because I have a minus here and minus 2 y sub I x of I raised to power b, and then plus 2 a summation x of I equal to 1 to n, and this is xi raised to power b, so I get minus and plus, then I have a 2, then an a, that's what I've written there. Then I have xi raised to power b here and xi raised to power b, based on the same powers I add, I get 2b. That's equal to 0. So that's equation number 1. And from here, what do I get? Again, I get 2, then a minus, then y sub I, and then multiply this whole quantity here. So I get minus 2 summation I is equal to 1 to n, y sub I. So a is there, so I'm going to take a outside because a is a constant now. So I'm going to get y sub I, x of I raised to power b, log of x of I. That's what I'm going to get. And then plus 2a squared, because I'm going to get 2, then a, then minus becomes plus, so 2a squared. All I'm doing is expanding the summation here. 2a squared is outside the summation, and what is inside the summation? I'll get xi raised to power b, xi raised to power b, so it will be xi raised to power 2b, and then log of x of I. And that will be equal to 0, and that will be the second equation which I will get. So all I'm doing is simply expanding these two summations here. Now you can very well see that I can just get rid of this 2 because I can divide by 2 throughout. I can also get rid of this 2 here because I can divide by 2 throughout because the right hand side is 0. I can also get rid of one of these a's here. And the reason why I'm able to get one of these rid of these a's here, because a's I'll have to assume that a is not equal to 0, because if a is equal to 0, then I have y is equal to 0 as my regression curve. So I'm going to assume that a is not equal to 0. That's what I'm looking for as one of my solutions. So I can get rid of these a. Now the good thing about this is that what this is going to do, if you look at this particular equation 1 here, that I can get a in terms of b, because a is only here. There's no a in this part, there's no a in this summation, but a is only here. So I can write a in terms of b, substitute it back in here, and I'll be able to get a one single nonlinear equation. So rather than having to solve two simultaneous nonlinear equations, I'll have to solve only one. So let me go ahead and write down the expression for A. So from equation 1, the expression for A is turning out to be summation y sub I x of I raised to power b divided by summation xi raised to power 2b, I is equal to 1 to n. So that's what we're getting for the value of A. So that means that A is explicitly known in terms of B. So keep in mind that this doesn't mean that we know the equation for A explicitly. We only know A explicitly only after we have calculated B. So what I'm going to do is I'm going to substitute this formula for A, which is in terms of B, in the second equation, so that I can, rather than having to solve two simultaneous nonlinear equations, I'll have to solve only one simultaneous nonlinear equation. So this one becomes minus y sub I x of I raised to power b log of x of I. So that is from the previous equation, I is equal to 1 to n. Then plus A. And A is this. So I'm going to substitute this value of A, wherever there's an A in the second equation. I is equal to 1 to n y sub I x of I raised to power b divided by summation I is equal to 1 to n x of I raised to power 2b. And then what is left? The other summation is left. I is equal to 1 to n xi raised to power 2b times log of x of I equal to 0. Now this might seem to be too complicated or too lengthy and things like that, but you got to understand that now you have a single nonlinear equation. The reason why it's nonlinear because you have xi raised to power 2b and xi raised to power b. That's what makes it nonlinear. But you can see that this is simply this whole equation here. Everything is known in this particular equation except for the value of b. All the xi and y sub I values are known because they are simply the values of the data which is given to me. So f sub b is equal to 0. So this is some function. This left hand side is f sub b. So this is some function of b. So I can use my bisection method, Newton-Raphson method, secant method, and things like that to find the root of this equation, which will give me the value of b. And once I have the value of b, I can go back here. So once I have the value of b, I can go back here and be able to find the value of a because I know the value of a explicitly in terms of the b constant. So that's how you derive the constants of the power model A and B. And that's the end of this segment.